We are talking about the natural phenomena due to dispersion, refraction, and scattering of light. The first natural phenomena that we are talking is the formation of rainbow formation, and that is due to the dispersion and refraction of light. So when it rains and small water droplets are floating in air, sun rays pass through those droplets. When they are incident on the water droplet, light passes from air to water. That means from a rarer medium to a denser medium. So, dispersion of light occurs. In water, red color bends the least, whereas violet color bends the most. Then inside the water droplet, there is total internal reflection, like this, and finally when light comes out of the water droplet, there is again refraction. So there are three things that are happening here. First, we have dispersion of light. That means different colors are bending at different angles. Then here we have internal reflection. And finally, here we have refraction. So due to these three phenomena combined, rainbow is formed. So in the examination they might ask you the question, how rainbow is formed or why rainbow is formed. So these three phenomena, dispersion, internal reflection, refraction. Rainbow is always seen on the opposite side of the sun. So if you see a rainbow in the morning, you will see in the west direction, and if you see the rainbow in the afternoon, it will be in the east direction. And there is a specific time in which you can see the rainbow, because the angle of incidence of sun ray is also very important, and for a specific angle only you can see the rainbow. So this was the first phenomena, that is rainbow formation. It was dispersion of light. Dispersion of light. The second phenomena is the atmospheric refraction. Due to atmospheric refraction, twinkling of stars occur. Now let us see why a twinkling of star occurs. There is atmosphere around the earth, and this atmosphere being in the gaseous state, it's not stationary, it is continuously moving. So when the starlight enters into the atmosphere, it bends. So if this is the star, When the light from the star, it comes near the boundary like this. This is vacuum and this is atmosphere. It bends towards the normal, but this bending is continuous bending because the layers of atmosphere, the air is thicker near the surface of the earth, whereas it is thinner if you go at higher altitudes. So what happens here, the apparent position of the star is slightly higher than its actual position. And also, as the atmosphere is a dynamic proposition, that means there are air currents which are flowing in the atmosphere. And why does this happen? Let us consider, if there is a flame over here, then the air just above the flame will be hotter, whereas air further up will be cooler. So there will be convection currents forming in the atmosphere. That means the cooler air will flow in the downward direction and hotter air will move in upward direction. So if you look at the air in this area, it will be continuously moving. Similarly, the same phenomenon happens in the atmosphere to a very larger scale. That means the air in the atmosphere is continuously moving and the sections of air are colder and sections of air are hotter. So the refractive index is also continuously changing. If the air is hotter, then we will have a lesser refractive index, and if the air is cooler, then we have more refractive index. So if we have more refractive index, we will see more bending, and if we have lesser refractive index, we will see lesser bending. So the light rays will bend lesser or more depending upon the section of air they are passing through. So physical conditions of Earth's atmosphere, as they are changing, they are not stationary. The light coming from the star goes on varying slightly. So the apparent position of the star will also fluctuate. It will not remain the same. Sometimes the star will be seen here, sometimes the star will be seen here. So the position will be fluctuating. Also the amount of light coming from the star will also change. That means brightness will also change, and that will give us the twinkling effect. And stars twinkle, but planets do not twinkle, because star is a point source of light, because they are very distant from the earth. They are seen as a single point, whereas if we look at a planet, although they are smaller in size, they are very near to the earth. That's why we see the planets as disk of light. Hence you can consider the planet as a collection of point sources. Each point in that collection, it flickers, fluctuates, twinkles. But as there are many points together, a collection of point sources, the average light coming from the planet always remains the same. Hence, stars twinkle, but planets do not twinkle. Stars twinkle, but planets do not twinkle. This is the reason. So, this is the phenomena. Then there is advanced sunrise and delayed sunset. What happens when sun rises? So if you are looking at the sun, suppose here is the sun, and you can say that this is the horizon and the sun is below horizon. The light coming from the sun, it bends towards normal due to atmospheric refraction, and the person sees the sun slightly higher than its actual position. So even when the sun is below horizon, the person can see the sun almost 2 minutes before it crosses the horizon, and this is due to the atmospheric refraction. So vacuum is a rarer medium, whereas the atmosphere is the denser medium. So when light enters in the atmosphere, it bends slightly towards normal. Hence the apparent position of the sun is slightly higher than its actual position. So sun is visible even when it is just below horizon. Same thing happens after sunset. Even though sun goes below the line of horizon, it is visible for 2 more minutes due to the refraction of light through atmosphere. Atmosphere is a denser medium than the vacuum. So this was about the atmospheric refraction. We saw the twinkling of star, advanced sunrise and delayed sunset. Then there is a scattering of light. What do you mean by scattering of light? When the light falls on very small particles, these small particles change the path of the light. If the particles are bigger than all the wavelengths of visible light, they scatter all colors. As we have seen, in case of smoke, small water droplets, suspended particles of dust and molecules of air. So when in the canopy of the forest we can see the path of sun rays become visible. That is called Tyndall effect. But most of the atmosphere is made up of nitrogen and oxygen molecules, and these nitrogen oxygen molecules, they are very small in size, so they scatter blue light more than the red light. The color of the scattered light depends on size of the scattering particle. So very fine particle, that is oxygen nitrogen molecule, mainly scatter blue light, while the particles of larger size, they can scatter all the colors. So as the blue light is scattered more in the sky looks blue, whereas red light is scattered the least, and that's why the danger signals are red, because red undergoes minimum scattering, so it is visible from very large distances. This is the same reason why sun appears red at sunrise and sunset, because during sunrise, as we have seen, the sun rays have to pass larger distance to the atmosphere than when on the midday sun rays travel only this much distance, whereas at the sunrise or sunset they cover a larger distance to the atmosphere. So when the distance is larger, the blue part of the spectrum is scattered away and only the red part of the spectrum remains undeviated, unscattered, and that's why sun appears red at sunrise.